Welcome to This Explainer. I am absolutely pumped to take you on this journey today. We're going to bridge a massive gap. The gap between the incredibly tactile hands-on gear we all love messing around with in the studio and the cold, hard, fascinating mathematics of digital audio that literally make modern music production possible. Whether you're a purist tweaking knobs on a vintage synthesizer, or you're someone agonizing over sample rates in your DAW, today we are going to demystify exactly what's happening beneath the surface.
Here is our roadmap for today's explainer. First, analog versus digital sense. Then, translating sound into numbers, followed by the magic of sampling and quantization. After that, we are going to debunk the 19.2 kHz audio myth, and finally, help you find your perfect workflow. Section 1, analog versus digital synths. Okay, let's dive into this. So, with analog synthesizers, the true lifeblood comes from physical hardware components. Right? We're talking about real physical electrical circuits, voltage-controlled oscillators, and filters. Because everything is physical, analog inherently introduces these gorgeous, subtle variations. The pitch might drift just a little bit, no two takes will ever sound exactly the same. It's warm, it's bulky, and it's beautifully imperfect. Now, on the flip side, digital synthesizers completely swap out those physical circuits for DSP, digital signal processing algorithms. Digital gives us extreme precision, absolute rock-solid stability, and incredible convenience of just pulling up a preset. Plugins like Serum represent this world perfectly. They're super portable, cost-effective, and they give you a massive sonic range that would be literally impossible to build with physical hardware.
But here is the secret that modern producers absolutely swear by. You don't actually have to choose just one. You can embrace a hybrid approach, mixing analog's natural aliveness with digital's surgical precision. Think about it. If you want a tight, clean, punchy bass line to anchor your track, digital is usually going to be your best bet, for sure. But if you've got a soaring, high-registered pad or a lead synth that really needs to feel human and expressive, route that through an analog unit. You can even find hardware that literally marries the two together, like Arteria's Freak series, which pairs digital oscillators with those warm, gritty analog filters.
Section 2, translating sound into numbers.
It really begs a fundamental question, doesn't it? What actually separates an analog signal from a digital one at the microscopic level? Well, an analog signal is continuous. It flows infinitely between states, exactly like a continuous electrical voltage. But a computer? Oh, a computer hates continuous. A computer needs discrete, exact, hard numbers.
To really wrap our heads around this, we have to look at how computers count. Computers only understand the most basic form of information, yes or no, on or off. We represent this with a 1 or a 0. This is the base 2 binary system. In our everyday base 10 decimal system, a number like 55 simply means 5 10s and 5 1s. But in binary, we use powers of 2. So to get the number 55 inside a computer, we combine a 32, a 16, a 4, a 2, and a 1. That gives us the binary word 110111. When we record audio, we are literally taking a wild, continuous voltage and forcing it into these rigid binary words at incredibly precise, rapid intervals.
Section 3, the magic of sampling. Now, this is perhaps the single most important concept in all of digital audio, the Nyquist theorem. Discovered by Harry Nyquist over at Bell Labs, this rule proves that we actually do not need infinite points of data to capture an analog wave perfectly. The theorem basically says that a sampled waveform contains all of the original information with absolutely zero distortion as long as your sampling rate exceeds twice the highest frequency in that waveform. I really want to let that sink in for a second. It is a mathematical rule of the universe. If we sample fast enough, we retain 100% of the detail. No information is lost between the samples. None. Zip.
And this brilliantly illustrates the dark side of Nyquist's discovery. If you fail to follow his rule, if you don't restrict your input bandwidth, and you try to sample a frequency that is just way too high for your sample rate, you don't just lose information, you actually gain false information. This is called aliasing. Notice how, when the sampling pulses just can't keep up with the fast-moving waveform, the computer connects the dots incorrectly and creates a totally false, lower frequency waveform, an alias. In audio, this creates really awful intermodulation distortion. So to prevent this, we absolutely must use filters to block out super high frequencies before they ever even reach the digital converter.
Section 4, quantization, measuring the wave.
So, quantizing is the process of assigning a physical voltage quantity to a binary number. And because we are forcing a continuous wave into fixed binary steps, there is always going to be an error. It's just a question of how small we can make that error. Think about it. An 8-bit system gives us 256 possible voltage levels to choose from, whereas a tiny 3-bit system limits us to only 8 levels. If the actual analog voltage lands right smack in between two digital steps, the computer just shrugs and rounds to the closest one. This rounding creates a discrepancy known as quantitation error, which actually sounds like a subtle white noise added underneath your track. The more bits you have, like 16-bit or 24-bit, the millions more divisions you have, and the vastly, vastly more accurate your recording becomes. Let's see how this actually builds out in hardware circuitry. How on earth does the converter quickly figure out which binary level matches the voltage? Well, it uses a genius technique called successive approximation. I want you to think of it exactly like an old-school gold miner using an assay scale. The converter evaluates the sample by placing its largest digital weight, its most significant bit, on the scale. If that digital weight is heavier than the analog voltage, it takes it off. If it's lighter, it keeps it on. Then it moves to the next smaller weight, having it every single time until it gets all the way down to the smallest possible weight. It does this step-by-step for every single bit, for every single sample, thousands and thousands of times a second. It's a truly magnificent feat of engineering.
Section 5, the 1900 2 kHz audio myth. All right, gear up for this one. A lot of salesmen will try to tell you that a 192 kHz sample rate gives you better resolution or more detail, but as Dan Lavry, one of the absolute pioneers of digital audio converter design, points out, there is no need for such a system. Let's just be real for a second and look at the facts. Human hearing maxes out around 20 kHz. The absolute most exceptional human ear on the planet cannot hear past 40 kHz. Musical instruments do not produce frequencies up there, and microphones certainly do not capture them.
Comparing these rates, the truth becomes totally undeniable. Based on the Nyquist theorem we learned about earlier, to perfectly capture a 20 kHz human hearing range, we only need to sample at slightly more than twice that rate. So around 44.1 to 60 kHz is mathematically optimal for 100% detail retention. Cranking the sample rate to 192 kHz adds zero audible information, literally none. What it does do is create excessively large, bloated files and puts a massive computational drain on your processor. But here is the real kicker, the part that surprises a lot of people. Operating at 192 kHz actually decreases your converter's accuracy. Why? Because of those gold miner scales we just talked about. The faster you force the converter to weigh those bits, the less time the analog components, like capacitors, have to properly charge and settle. So the crucial point is this. There is a permanent mathematical engineering trade-off between speed and accuracy. If you run a converter at a blistering 100 MHz, you might only get 8 bits of accuracy. Slow it down to 50 Hz, and you can get near 24 bits. Forcing your system to output 192,000 samples per second compromises your accuracy, actively introducing distortion just to capture supersonic frequencies that bats can hear, but you cannot. Now, to be fair, internal oversampling inside the converter hardware is super useful for anti-aliasing filters, but the final audio file sitting on your hard drive does not need to be, and mathematically shouldn't be, 192 kHz. Plus, downsampling it later just discards all that supersonic data anyway.
Section 6. Finding your perfect workflow. Now, what's really fun is how you can directly apply this dense science to who you are as a creator. If you're the traveler, always working on a laptop in a coffee shop or stuck in an airport, lean completely into the digital realm. The math proves that digital is flawless at retaining information. Use those plugins for ultimate portability and instant recall. On the other hand, if you're the vintage fan, invest in that bulky, awesome, tactile analog gear. Let the physical circuits give your music those unpredictable, warm imperfections. If you identify as the audiophile, well, you now have the hard science to back up your workflow. Trust the Nyquist math. Save your hard drive space and your CPU processing power, stick to standard sample rates, and confidently ignore the 192 kHz snake oil. Or be the modern creator and embrace a true hybrid workflow, using the flawless precision of digital audio to cleanly capture the wild, beautiful nuances of your analog gear.
You now understand exactly what happens to a sound wave from the moment a physical circuit generates it to the exact microsecond it's weighed and stored as a binary 1 or 0. You are fully equipped to make much smarter decisions about your gear, your sample rates, and ultimately your own sonic identity. So I want to leave you with this final thought as you head back to the studio today. Armed with this new knowledge, does the future of your music lie in the mathematical perfection of digital code or the beautiful, unpredictable flaws of physical circuits? The choice is entirely yours.
Keep experimenting, keep learning, and I'll catch you in the next explainer.